Hello, everyone. Thank you for joining us today for this DOE USDA Consensus Program webinar on NETL's cost of capturing CO2 from industrial sources and industrial carbon capture retrofit database. Really excited to host this webinar today. For those of you who don't know me, my name is Alex Krauka. I'm a Seattle-based consultant for USDA's Consensus Program. This topic is incredibly important and really exciting. There is sometimes some controversy around CO2 capture when it comes to power generation. However, when it comes to industrial sources, I think most everyone can agree that the importance of capturing CO2 or capturing emissions from these hard to decarbonize areas is incredibly important. And CCUS will be one of the main ways to reduce emissions from industry. But before we get too deep into the weeds, I'd like to introduce USDA's Executive Director, Ms. Sheila Hollis, to say a few words about the association.
Thank you so much, Alex. I'm Sheila Hollis. I'm the Acting Executive Director of USDA, and it's my pleasure to participate in this series of outstanding programs that DOE and USDA have been working on for the entire year or two. And a little bit about USDA. We've been around nearly 100 years. It was formed back in the day when just beginning of electricity to serve America. And the rest in other parts of the world. We started off basically as a convening type of organization where major players in the electricity arena gathered to meet and think great thoughts and put out additional papers and that sort of thing. But as time went on and energy evolved and the dependence of the world became so obvious with respect to the availability of energy throughout the world, our role really evolved along with what was going on beyond the confines of USDA. Basically, we knew that there had to be communications about what all was being done in energy, the development of natural gas, the need for awareness of CO2 related issues, hydroelectric, and a variety of other sources of energy. So with that, we moved into an arena where we were providing information. This is pre-Zoom time, of course, so meetings in person, that sort of thing. But then another thing happened, which was of such tremendous significance. It really evolved and forced us to really expand our activities in a very, very different way. And that was the fall of the wall. And when the wall fell, the world opened up. There was a tremendous need for energy in parts of the world where they had been behind the Iron Curtain and was in an extremely primitive state without getting into the very nitty-gritty details of that period. But the bottom line is that working with USAID and the State Department, USDA was called upon to participate and aid in the transition to a better, cleaner, more capable of serving the needs of the people in those countries. So that really began a different scenario for us. Additionally, as we evolved, our meetings expanded, and we were doing many more things in a variety of different ways. And of course, now with Zoom and all, it's a whole different world. But it's an honor to be with you here today. We hope that you'll look at the USDA website. We're putting on a massive conference day after tomorrow in person for a change, first time in 3 years. And there will be a follow-on from that, I'm sure, with the availability of speeches and so on, both in written form and perhaps hopefully available to be viewed after it's been filmed. So with that, I turn it back to Alex. We're terribly proud to be associated with this great program. The need to capture CO2 and store it is central to what we need to basically survive in the world we're operating in today. And so with that, I turn it back to Alex, and just delighted to listen and play a small role in welcoming you and hoping that this is beneficial to you and also introduces you more to USDA and what we do. Alex?
Great. Thank you so much, Sheila. Really appreciate you taking the time out of your day to join us. and always great to see you, and look forward to seeing you in a couple days here. Moving on to kind of what brings us here today. This effort is being produced through what we call the Consensus Program. The Consensus Program is a cooperative agreement with the U.S. Department of Energy's Office of Fossil Energy and Carbon Management that seeks to educate the public, policymakers, industry, and other stakeholders and build a consensus on the benefits of and requirements for CCUS and other carbon management technologies such as carbon dioxide removal, methane emissions mitigation, blue hydrogen development, sustainable domestic production of rare earths, critical minerals, and much of what falls under the carbon management umbrella. We do this through a series of activities such as briefings and webinars like the one we're hosting today. We host workshops on occasion, both in person, virtual, and hybrid as well. We also put out various technical reports and white papers in collaboration with some of our subcontractors. And then we have a monthly news clips to help keep our stakeholders informed. If you'd like to subscribe to our mailing list, please feel free to email my colleague, Michelle Littlefield at mlittlefield@usda.org. Just a quick logistical note. This webinar is being recorded. We will post a copy of the presentation as well as the recording on our event page. Please give us a day or two to do this. Sometimes it takes a little bit for the videos to upload. We plan to have Q&A at the end of the webinar. Please use the Q&A box at the bottom of the Zoom window for any questions, comments that you may have, and we will get to as many of those as possible. Now, on to our speaker for today. We have Sydney Hughes, engineering support contractor at the National Energy Technology Lab. Sydney has 7 years of experience in the natural gas processing industry, where she served as a plant engineer, a processing engineer across multiple state territory, and finally as an operations and maintenance leader at a major natural gas fractionation facility. Since joining NETL in 2019, her work has focused mainly on post-combustion carbon capture systems and CO2 utilization technologies. Sydney has earned 3 degrees from Louisiana Tech University in chemical engineering, engineering and technology management, and an MBA as well. So with that, I'm going to pass it over to Sydney. And Sydney, the floor is yours.
Thank you. Let me share my screen. Oops, sorry. Head back to the first slide there. And let me know whenever you're able to see these slides, please.
You're good to go.
Okay, great. Thank you. So hello, everyone, and just echo the sentiment and thank USDA for allowing us the opportunity to present some of our work related to carbon capture in the industrial sector. Like Alex said, I'm Sydney Hughes. I, along with several NETL colleagues, helped to develop the report Costs of Capturing CO2 from Industrial Sources, which we're going to discuss today. So just a brief agenda of what we're going to talk about today. I'll start with the report and step through an overview of the objectives and pertinent design assumptions and financial methodology, followed by the cost results from the study. The report was the basis for the development of the public industrial carbon capture retrofit database tool, which was developed in large by my colleague Norma Kuhn and a host of several NETL employees. So we'll discuss that following the report data and even step through a little demo of the CCRD tool. We'll allow some time for questions at the end, so I appreciate you guys populating those questions in the Q&A as Alex instructed. So starting with the report, our goal with this was to estimate the capture costs at 9 representative industrial facilities. Those representative plants were not modeled themselves, but their size and resulting emission streams characteristics were established either based on literature, vendor input, or other NETL studies that have been previously developed where appropriate. The high purity sources of CO2 in this report are inherently 98 to 100% pure CO2 directly from the point source. The low purity sources range from about 13 to 27% CO2 depending on the source. And you can see how they're grouped in the table here between high and low purity, which I'll elaborate on a little bit more later. While those low purity streams do require further purification, besides just compression and possibly dehydration, they're still relatively high CO2 concentrations compared to a typical 4 to 13% CO2 flue gas stream from, say, a fossil-based power generation facility. We do evaluate capture costs for flue gas streams and power generation facilities in our fossil energy baseline study. My colleague Mark Turnell will be presenting on that next week, I think on February 2nd in another USDA webinar. So we look forward to that discussion as well. We use the emission streams from each of the plants that are outlined here in the table to quantify the cost of capture for each industrial plant. In most cases, we provide both greenfield and retrofit capture costs, but just wanted to point out that for the coal to liquids and gas to liquids cases, we only predicted greenfield capture costs as there are currently no CTL or GTL plants in the domestic fleet, and we would expect that any new builds in any industry would likely include carbon capture systems. So in addition to those, the iron and steel case, we considered a basic oxygen furnace steel plant, which is pretty common in the domestic fleet now, but they're really no longer being built. And for that reason, for our iron and steel case, we only included retrofit costs in the study. So some of the most pertinent design assumptions made in the study were related to the capture equipment and its associated capital costs. For the cases where we did project those retrofit costs, we applied a retrofit capture to our total plant costs formulated from greenfield estimates of the capture and auxiliary equipment. The retrofit factor is reflective of the difficulty to implement the capture equipment based on factors such as space constraints and tie-in coordinations. So for the high purity cases, we applied a 1% escalation to those greenfield costs to represent the retrofit costs. And for the low purity cases, we applied a 5% premium. We delineated between high and low purity CO2 sources by their purification requirements. So in some cases, only compression and associated cooling, along with possibly a little dehydration of the CO2 stream, was required. And then for the cases that required further purification, we called those the low purity cases in this study. We applied amine-based CO2 capture systems to those emission streams prior to that compression and dehydration steps. The low purity group in this study includes the cement and iron and steel cases, which use Shell's CANSOL post-combustion capture system, and then the refinery hydrogen case, which employs a Shell ADIP ultra pre-combustion capture system. So in 2021, Shell provided quotes for these capture systems, each at 90, 95, and 99% capture rates. Each quote that they provided included capture rate specific design so that specific equipment sizing and solvent performance could be applied appropriately to represent the cost implications of increasing capture rates. As for our financial methodology, NETL maintains a library of quality guidelines for performing studies and TEAs related to energy systems. The methodologies outlined in those QGAS documents were used to guide the performance and cost modeling for the cases in this report. For major equipment pieces such as the natural gas-fired boiler, the compressors, the Shell capture systems, vendor quotes were obtained and were scaled to fit the operating basis for each case. In 2 cases, we had small equipment pieces that were just a heat exchanger, a small heat exchanger, or a water knockout drum. And those equipment pieces were sized and their costs were estimated based on heuristic equations, as they represented a fairly unimpactful capital cost for their respective cases. All of the cases in the report include balance of plant equipment to support the capture systems, such as cooling water tower and the water circulating system, accessory electrical equipment to convert grid power to its appropriate users, instrumentation and control systems, and then costs associated with site preparation and operations buildings. So all of those ancillary costs were scaled from NETLs, eliminating the D rate of carbon capture retrofits. It's a study where the scale of similar cost accounts in retrofit or add-on applications aligns with the scale of those in this report. So lastly, we included incremental operating labor for each case to account for the additional staff requirement for adding these capture systems at the plants. So in the high purity cases where we only have compression and dehydration, we consider one additional operator. For the more complex purification and compression systems, like those in the low purity cases, we have 2.3 operators added to the plant staff. This incremental staffing requirement stems from the difference of labor forces between capture and non-capture cases in our fossil energy baseline series. I just wanted to note that for the iron and steel case, it was a little bit more complex, where we needed 2 capture systems due to the assumptions that the emission streams are of too great a distance to be aggregated into one capture system. So for the iron and steel case, we have 4.6 additional operators, so 2.3 per capture system. And then the resulting process models that we developed were used to estimate the cost of CO2 capture, which is calculated by the equation shown here. The model outputs helped us to generate the capital and fixed O&M costs and estimate the variable O&M costs for consumables. In addition, we use the predicted auxiliary power loads of the capture system and the natural gas consumption rate of the boiler, which was required to raise steam for solvent regeneration. We use those 2 factors to estimate the purchase power and fuel costs, respectively. So power costs were estimated at a rate of $60 per megawatt hour, and then the natural gas fuel costs were estimated at $4.42 per MMBTU. Fluctuations in purchase electricity and fuel prices were evaluated via sensitivity analyses, which I do plan to cover in an upcoming slide. So capital charge factor was used in that equation on the previous slide to bring the total overnight cost of the system to a levelized capital expenditure. NETL developed industry-specific financial scenarios to apply to each case in the study, and the financial parameters and resulting capital charge factors are summarized in this table. Each case considers a 30-year operational period, but various construction periods are considered for that capital expenditure. So for instance, the high purity sources require a 1-year construction period, as they're very little equipment and expected to be pretty low complexity when building. For the low purity sources, those that include the shell solvent-based capture systems, we allotted more time for construction, and thus the capital expenditure is distributed over 3 years. So sensitivity to the resulting capital charge factor is provided within the report so that users can see the impacts of differing financial scenarios on the overall cost of capture. So the cost of capture report results from our report are shown here, where you can see a clear cost difference between the high purity sources to the left of the dotted line and the low purity sources to the right. It's obvious that plants with CO2 separation steps that are inherent to their base processing provide a cost advantage over those plants whose emission streams require more CO2 separation. So while the low purity sources are all relatively similar in cost, the high purity sources reflect at a high level the impacts of economies of scale. Since very little equipment is required in any of those high purity cases on the left-hand side, simply because they're 98 or greater % pure CO2, it's relatively cheap to remove the balance of water that's in those streams just to meet the CO2 pipeline specifications. The reason for stark differences between the cost of capture, say comparing ethanol and ammonia, is related to the quantity of CO2 captured. Since the cost of capture represented as a normalized figure down to the dollars per ton CO2 basis, and then the individual cost components don't increase linearly, the point sources with higher CO2 flow rates are inevitably cheaper to decarbonize on a per ton basis. The same phenomenon is noticeable whenever you compare the low purity cases at 99% capture to those at 90% capture. And on that note, we recognize that the notion of lower costs at higher capture rates may be somewhat counterintuitive. So just for explanation there, as mentioned before, Shell provided specific cost and performance quotes for each of the capture rates evaluated. Those quotes came with a -25 to +40% capital cost uncertainty, and alongside the cost uncertainty that comes with a class 4 estimate, AAC class 4 estimate, which is applied in our study, it's reasonable to conclude that normalized costs of capture, as well as the capture system's barrier-erected costs, are essentially the same at 90 and 99% capture rates. The plots shown here indicate the capture system BEC at each capture rate, along with the vendor's quoted uncertainty range as error bars, and that's just to demonstrate the same conclusion. So acknowledging the potential variation in design assumptions, we included in the study several sensitivity analyses related to select parameters. Here, I wanted to highlight two that are often a hot topic of conversation, especially in more recent times, and that's the purchase power and the natural gas prices that we used. So all of the cases in the study meet auxiliary load demands via purchased electricity. And in the low purity cases where steam is required for that solvent regeneration, we use natural gas to fuel a boiler. So the cost impacts from changes to those prices of those two consumables is provided via sensitivity in the study. But of course, in some applications of carbon capture, alternate heating and power supply options may be available or may be considered for install. For instance, combined heat and power production is not considered in our study, but might serve as a more valuable option for project heating and power supply based on, the scenarios at the host plant. So the results of the industrial capture analysis highlight that while some industrial facilities may be cheaper to decarbonize on a per ton basis, the overall impact of those decarbonizations may prove a little less beneficial than those where normalized capture costs are higher. Of course, the costs estimated in the study are representative of a steady state operation of a base plant that was defined by our own assumptions, not indicative of the cost of capture of every carbon emitter in any given sector. However, if you compare the capture costs of one average industrial plant to another, viewing the annual sector emissions for those plants could also provide some valuable insight. For instance, though iron and steel and cement represent the two highest normalized costs in our study, their annual emissions profiles indicate that their impact on industrial decarbonization is greater than that of less expensive sectors like maybe ethanol or ethylene oxide. Cheaper plants like ammonia and natural gas represent possibly easier to capture streams with potentially very large reductions in domestic emissions. So as stated, the costs that are presented in our report are really representative of a steady state model under specific design assumptions. So like the sensitivities to purchase power and natural gas prices, the report also provides at a high level a sensitivity to the representative plant size and the resulting CO2 emissions that are available for capture at each plant. So curves like this one are generated for each industrial case in the report, as the representative plants in the study are not indicative of the very many plant sizes that we see in each industry. And that brings us to the very valuable tool that was developed as a companion to the industrial capture study. That's the Industrial Carbon Capture Retrofit Database, or as we like to call it, the CCRD. This is a publicly available tool. It's housed in an Excel workbook, and I promise to show you guys that in a few minutes. It estimates the cost of capture for a set of industrial facilities, and it can be used to predict capture costs for entire industrial sectors. It allows for scenario manipulation and comparative analysis based on a set of user input assumptions, and it quickly predicts the cost impacts of varying those assumptions. Users are able to define variables themselves, choose from the default variables, which were sourced from the industrial capture report, or for some parameters, they can select state level averages. In some of the cases, some of the cases in the industrial capture report are not included in the CCRD tool. And that's simply due to either lack of plant data or emissions data for those industrial plant types, or just a low consensus in the domestic fleet where it was not really appropriate to apply some of our design assumptions to those that list of plants. So for instance, just an example, CTL and GTL plants are obviously not included in the CCRD because they're non-existing. So it doesn't make a lot of sense to project retrofit costs for plants that don't currently exist. So the results of the CCRD tool can be used to perform a host of comparative analyses. That's really the backbone of this tool. As shown here, we can use it to predict the additive cost of capture for an entire industry based on our assumptions as a function of cumulative CO2 capture, or it's really helpful in generating quick analyses related to market conditions, like here, where we show in green markers the same analysis as the black markers, black and orange markers, but with 2022 conditions, where natural gas soared over $8 per MMBTU, where we were originally assuming $4.42. The CCRD can also be used to evaluate a range of plant sizes and their associated costs. It can predict their mean and median costs for comparison to other reports or our report. It allows for an apple-to-apple comparison of costs whenever year dollars and financial assumptions are all set to constants. For instance, here we're showing a range of plant sizes along with their reported, the cost of capture in our report, but all at 2022 conditions instead of our report's December 2018 conditions. So it's really helpful in making these quick comparisons. And then lastly, just before I jump into a demonstration of the tool, it does allow us for a bit better understanding of location-based impacts on capture costs. Several of the parameters can be manipulated to represent state defaults or state averages. This functionality is really important when you're considering capture costs alongside transport and storage infrastructure and the costs associated with T&S. So the industrial CCRD tool is really handy just on so many fronts. It does come with a built-in user guide, so it gives potential users just the best experience that they can get when running the tool. And with that said, it is important to note that we outline all of our design assumptions to the best extent that we have possible, because the results of the CCRD and the industrial capture report are not really meant to be indicative of actual CO2 capture costs at any industrial plant. The report, as well as the CCRD user guide, serve as tools to demonstrate the capture cost development practices and provide representative capture costs of average plants. And then the CCRD tool itself is very valuable for comparative analysis, maybe between various plant operating conditions or financial scenarios, or to compare to one industrial sector to another. But overall, the results from each of these should be used and considered anecdotal anything that would be used for project authorization or budgeting decisions would require significant additional study, such as a feed study, in order to more accurately quantify the capture costs. So I provided links to the report, the CCRD user guide, and the CCRD tool itself, all for your reference. They're going to be available in the PDF slide deck that USDA provides on their website following the webinar. So while I'm here, I just want to take a quick few minutes to demonstrate the tool for all of you. Let me share a different part of my screen. So whenever you open the CCRD tool from the link that I provided, it will open as a download Excel file. The first pop-up you'll see tells you that you have to enable, or ask you if you want to enable macros. You must enable macros for this to work. That's why it's here in bold. And then when you click Start Program, it wants to make sure that you've read at least section 2 of the user guide and understand the limitations of the tool, which are largely related to the slide I just presented and talked about. Following that, whenever you open the tool, it immediately opens to a user input guide where you can select either default values, user input. If you select the default, those are pre-populated values. If you select user input, you are able to input what capture rate you want or what capacity factor that you want. So several of these variables can be set to user input or state averages or just the default, which is sourced from the industrial capture report. The summary tab provides a summary of the results from your analysis, very high level results here. And if you want to see the individual industry results for your specific set of user inputs, there are results tabs for each of the industries down here. Lastly, there is a charts function which can plot several of the pertinent results into charts for you just by sheer selection of what you want on the axis. For instance, we can do cost of CO2 captured and incremental COP. And up here at the top, you can select which case you want to see. So natural gas versus ammonia versus cement. Just to show one of the industry specific results tabs, we have the cement here where it lists the facility name, location, ID, some of the high level values that the tool spits out, the CO2 captured, the cost of CO2 capture, the cost of CO2 avoided. So really just a lot that you get to see here in the tool. And with that, I will flip back to the presentation. And that concludes what I had to present today. And I think I've left us 20-25 minutes of time here for questions and answers. So before I take any questions, I just wanted to say thank you to Tim Fout and Eric Grohl at NETL for helping all of us develop this report and this tool.
Great. Thank you so much, Sydney. This has been an awesome presentation, and we've got a bunch of questions that have come in. So I'm going to start with one that was actually emailed to us beforehand. What were the differences in the aiming capture operating conditions between 90% and 99 capture? In particular, was the lean loading into the absorber the same as suggested by the reference cited, or was a lower lean loading used for 99% capture? And were different or the same absorber packing heights assumed?
Yeah, great question. And I hope that I did answer this in the presentation whenever we presented some of the design specs, but yeah, we can't provide the actual loadings and absorber configurations and whatnot because those are proprietary to Shell, but they did provide to us capture rate specific designs for each of these plants and each of the capture rates. So that comes with specific lean loadings and associated reboiler duties and specific column heights and packing configurations and everything. So yeah.
Great. Thank you, Sydney. Sorry, just had a person come to my door, unfortunate timing and part of the issues of working from home. So the next question that we have is, how applicable would these cost estimates be for other developed economies in the UK, Europe, Japan, etc.? And then what about countries like China and India?
Yeah, that's a great question. Of course, your economics are going to be different based on your location and your industry. So that's going to play an important role in the development of that capital charge factor, which we use to apply to the total overnight cost to get that levelized capital cost. In addition, we had to assume really generic conditions for things like permitting and the time that it takes to get that done. We had to make assumptions about natural gas price and the purchase electricity price, which would greatly vary depending on your location. And so all of those things, we did our best to provide a sensitivity analysis to them. And if not, there are methodologies for how the capital charge factor and the purchase electricity and natural gas pricing is applied to the cases. We did our best to be as forthcoming with all of our development as possible so that users could make manipulations where they were able to. And just to elaborate on that just a tiny bit more, we include our O&M costs down to the consumable rate. So we tell you exactly how many megawatts of energy are needed or of power are needed and how much natural gas is needed per day for the boiler. So we got down to as much detail as we could so that users could possibly back out and apply their own financial situations to the results.
Great, thank you. Next question, why is there such a difference between ammonia and refinery hydrogen costs? Aren't they both using steam methane reformers?
Yeah, that's a great question. So the ammonia case in our study is only looking at the ammonia stripping vent. So it is a very high purity stream. It's like 99% CO2. We didn't consider capture from the primary reformer in the ammonia plant as part of the study, only because it is so similar to other costs of capture that we have either in this study with the refinery hydrogen case or in other studies where we consider capture costs. So yes, to totally decarbonize an ammonia plant, you would have the additional capture costs associated with that primary reformer. But for this particular study, we only looked at the stripper vent. Now, to add to that, the CCRD tool, the Excel tool, actually does have two capture streams for the ammonia plant where we do estimate the capture cost of that primary reformer stream in addition to the stripping vent stream.
Got it, thank you. And then we have a comment that the costs for geological sequestration are vital. Do you know the known costs for large-scale bedded salt cavern sequestration?
I don't, but that is absolutely true. Your end-use costs can dramatically affect the outcome of a capture project in any situation. So yeah, sequestration costs would be an added cost on top of these capture costs, and we specifically did not project those additional costs for CO2 in use so that they could be added on a user specified basis.
Got it. And then kind of sticking with capture costs, how about 85 to 90% capture rate at a lower capture cost? Is there an optimum for special systems and solvents?
Another great question. Wow, these are really good. Yeah, we saw from this analysis that higher capture rates were more cost beneficial. However, and there's another question in the chat about, or in the Q&A about this, so I'll just address it. We didn't consider the emissions that were created from the natural gas boiler that was used for the solvent steam. And so your cost avoided is likely not beneficial at higher capture rates. And so that's something that would have to be addressed in future work and is slated hopefully for funding with NETL for us to look at in the future. And just like with many of the design assumptions that I went over, we had to make a lot of like very overarching decisions about how we wanted to present this. And it came down to, we wanted to look at very similar capture systems. They're all amine-based systems. Yes, the refinery hydrogen is technically a pre-combustion system, but they all come out to pretty equivalent costs. And we did that because we were really trying to show a comparative analysis here, not necessarily to say, this is going to cost you $70 per ton, but so to say ammonia stripping vent or a natural gas processing plant is likely cheaper to decarbonize on a per ton basis than a cement plant or, a fossil energy plant, if you wanted to lay this beside our fossil energy baseline capture costs. So.
Got it. Thank you. More coming in here. Did you consider complexity and integration factors for different sectors? And then what was the range for the Lang factor ratio of total capital cost to total equipment cost?
Oh, that's one I'm not going to be able to answer off the cuff. But I can provide an answer to that in a follow-up. But just to be clear, we provide all of the total capital costs and total plant costs for every case. So you could easily look in the tables and get that from the report. Sorry, what was the other question that I think you asked?
Sorry,
it had a number 2.
Yeah. Did you consider complexity and integration factors for different sectors?
Yeah, that's another one that's easily answered, but likely leads to future work. So we did not consider an industry specific complexity factor. We applied a higher retrofit difficulty factor whenever there were low purity cases where we had those solvent based capture systems, just because more equipment means more complexity and longer project timelines and harder tie-ins. But this is something that's been brought up numerous times whenever we've had discussions about this report, especially in industries where their existing plants take up huge amounts of space and there's not a lot of adjacent plot plan, or the ground is not suitable for supporting heavy pieces of equipment or whatnot, and has to be significantly overhauled. So we didn't go into specific retrofit difficulties for every single industry, but we do provide a sensitivity to the retrofit factors that were applied. So if you knew that you had a site that was going to be 20 to 30% more complex for implementation of these capture systems, every single case has up to 1.5 so 50% difficulty factor added in that sensitivity analysis.
Got it. Thank you. And I see your colleague Travis Schultz has also unmuted himself. I don't know, Travis, did you want to add to Sydney's answer there?
No, I'm okay.
Okay, great. Thank you.
Travis, you can butt in anytime you want.
And Sydney, could you please restate the cost of CO2 avoided definition, please?
Yeah, I don't have it in the presentation, but I'm going to flip back a few slides just to use the cost of capture equation as a demonstration. So here in the cost of capture equation, the cost avoided, as far as our studies define it, would be in the denominator of this equation, it would be tons of CO2 captured minus the tons that were generated from that natural gas boiler that we had to add. And so it's essentially the same exact equation. It's just divided by a smaller number.
Okay, thank you for clarifying that. It looks like some of the questions that were up have been answered in the chat. So if anyone would like to see what the answers for those were, please feel free to take a look. We do have a little bit of time scheduled here in case anyone has any last minute questions, but I know I don't think anyone's ever complained about meetings or webinars ending early. So if we don't see anything come in here, we'll go ahead and move forward. Not seeing too much more. Sydney, thank you so much for taking the time to do this. This was really great. We had almost 300 registrants, at one point about 170 or so attendees, and most of the people are still here. So, you know, incredible amount of interest in this, and judging by over 20 questions and comments that came in, a lot of active participation. So this has been really great. Thank you.
Yeah. Hey, Alex, there was one more that has just come in the Q&A, and I wanted to make sure to answer it. It's from Ed Rubin.
Yep. Yeah, I see that. Do your avoidance costs include emissions from purchased power?
And this is another wonderful question that often comes up. It does not. These are not considered life cycle costs. It's not a life cycle analysis. It's just point source emissions. But we do hope to work with our LCA team at NETL and expand upon this analysis to look at life cycle costs. And I think the CO2 avoidance will come into much bigger focus whenever we look at those.
Most definitely. So with that, again, thank you, Sydney. Just want to quickly share our next webinar on a topic that you had mentioned earlier, that will be presented by your colleague Mark Turner, looking at cost and performance baselines for fossil energy plants. That webinar will be next Thursday, the 2nd at 1 p.m. Eastern. So hope everyone is able to join us for that. And with that, I will give everyone about 10-15 minutes back in their day. Sydney, again, thank you so much, and look forward to hosting you in the future.
Yeah, thank you, everyone.